Hello students, here I am going to discuss some important problems from alkanes chapter. Okay, so here in this case the first question is it is a dicarboxylic acid. This dicarboxylic acid on electrolysis actually. Okay, so generally here the sodium or potassium salts of the carboxylic acids, okay, for suppose sodium or potassium salts of carboxylic acids on uh, electrolysis we will get the alkane actually. Okay, here in this case it involves alkyl free radical, so that alkyl free radical combines with another alkyl free radical, we will get the alkane. Okay, so that is the basic idea of the coal base electrolysis reaction. Now here, this compound in coal-based electrolysis produce which compound, which product? Okay. So here in this case, it is an intramolecular coal-based reaction. Okay. As from the reaction mechanism, here the diradical is produced. The diradical is produced. Okay. For suppose this carboxylic acid COOH. Here this COOH. It's a potassium salt I am taking. Okay, so COOK, yes, COOK. This one in coal base electrolysis, aqueous solution of this compound in coal base electrolysis gives a initially diradical. This diradical converted to cyclohexene. Okay, now here in this case, here also diradical is produced. Okay, here also diradical is produced. Here in this case, the pi bond formation is not possible. Okay, pi bond formation is not possible because the formation of the strain ring. Okay, here in this case, sp carbon is not exist in a 6-membered ring because of the angle strain. Sp carbon must attain the 120 degrees angle, but here 120 degrees angle is not possible. Here it is a 120 degrees. So due to higher angle strain, this product is not formed in this reaction. Okay, so next here, this diradical combines with another diradical. Okay, as a result here we will get this anti-aromatic product. Okay, even though it is an anti-aromatic product, it is exist, but here this compound is not even exist. Okay, this compound is exist, of course, so not stable at low temperature. This compound is just stable, so finally here we got this product. Okay, now here see this one, it is another one compound. This one in coal-based electrolysis, what is the major product? Here in this case, it is a actually larger size ring. Okay, here in this case, total 10 carbons are there. In the 10 cyclic member ring, here there is a formation of the that means the sp carbon. There is the existence of the sp carbon in a larger rings. Okay, it is a cyclodecyne is exist. Cyclohexane not exist, but cyclodecyne or even cyclooctane is exist. Okay, so to exist the sp carbon in a cyclic ring, there should be requirement of the 8 carbons at least. Okay, it is a cyclodecyne. Okay, here 8 member, that means sp carbon is exist in this case. Even it is actually in a 8-member ring also we can see the triple bonded carbons. Okay, cyclooctane is also exist. Cycloheptine not exist, cyclohexane not exist because of the angle strain. With increasing more number of carbons here, there is a flexibility to exist sp carbon. That's why here we'll get the cyclodecyne, okay, or cyclooctane in case of the 8-membered ring. Okay, so here the answer is B actually. Here in this case, between these two compounds, this compound is a more stable compound. There is an anti-aromatic compound, unstable compound. Okay, But here in the above example, this compound not exist, even though it is unstable compound. Here finally we will get this product at low temperature. Okay, so that is a difference between these two uh, reactions. Okay, that's it. Or suppose very interestingly, just I got remember this one, COOK. Here COOK, this compound on coal base electrolysis. Okay, on coal base electrolysis. Yeah, first suppose see this one here. I am taking the pi bond at this position, so here in this case we'll get the diradical. So now here the product may be this one, um, cyclobutadiene, but here in this case this product is not formed. Why? Because this one combines with another diradical, so here we will get this product. Now between these two, which is a more stable compound? This is the more stable compound. Why? Because it is not an anti-aromatic, it is an anti-aromatic compound. This one is the least stable, so it is not formed as a major product. Here in this case this is formed as a major product. Okay, but here in this case there is no chance actually. Okay, so that's why here anti-aromatic compound is a final product, because it is not even exist. Okay, here both are exist, between these two it is a more stable. That's why here this dimer product is formed than the anti-aromatic product. Okay, that's it. And next let us discuss one more question. Yeah, which of the following cannot be prepared by Wood reaction in good yield? So actually here to prepare the product in a Wood reaction, so Wood reaction is not suitable for the tertiary halides, and Wood reaction is suitable for the preparation of the alkanes with a more symmetric structure, because in Wood reaction it is a combination of the two alkyl halides. Okay, for suppose ethyl chloride in Wood reaction produce a butane. Now here in this case only symmetrical alkanes we can prepare from the Wood reaction. Of course it is a symmetric alkane. It is not a symmetric alkane, we cannot cut into two equal halves. Okay, here in this case it is a symmetric alkane. By taking CH3 CH CH CH2Cl CH3 halide, we will get this product. Now here in this case it is not a symmetric alkene, so we cannot prepare this one by the Wood reaction. This one also cannot prepare by Wood reaction. Now here in this case it is a symmetrical, but here the tertiary halides CH3 CH3 Cl, tertiary halides in Wood reaction produce a disproportionation product as a major product. CH3 tertiary butyl radical involves. Now here two tertiary butyl radicals get disproportionation. Here C radical. Now here this H radical and C radical combines, as a result that isobutane is the one product. Now here by removal of by loss of the H radical, CH2 radical is C radical, so it is converted to CH3 C double bond CH2 and CH3. Isobutene is a product. Isobutene and isobutane disproportionation dominates than the dimer product. Okay, because here in this case combination of these two radicals becomes difficult because of the some strain in this compound. Okay, that's why this dimer product is not formed in a good yield actually. Okay, isobutane and isobutene are formed in a good yield. Okay, so here A, B, D are the answers. Okay, that's it. And next yeah, this one, you see this one. This one reacts with the H2. The product of the above reaction will be maybe racemic mixture or meso or diastereomers or constitutional isomers. So here I am taking this compound, the cyclopentene. Here methyl below the plane, that is a fixed geometry. Now here in this case this double bonded CH2. Now on addition of the hydrogen here, that becomes a CH3 actually. that becomes a CH3. Here in this case, this CH3 may be above the plane because this carbon is a sp2 carbon. This sp2 carbon converted to sp3 carbon. sp3, in that case, that methyl may be above the plane or below the plane. Here below the plane, here above the plane. Of course, here that hydrogenation, it is actually planar center. So about this planar center, here hydrogenation, okay, addition of the hydrogen takes place either front side or back side. That means here the methyl may be below the plane or above the plane. So here in this case, this is the cis isomer, it is a trans isomer. These two are the diastereomers. Okay, so in this case here diastereomers are the products. It's not a racemic mixture, it's not a meso compound. Of course, here in this case, this is the only one compound is a meso compound, but this compound is optically active, this compound is optically inactive compound. The relation between these two are the diastereomers. That's it. Now next, which pi bond will reduce first when above compound undergo catalytic hydrogenation reaction? Actually, in catalytic hydrogenation reaction, which are more reactive? Okay, here in hydrogenation, the reactivity, okay, is reactivity inversely proportional to stability actually. How the stability of the alkenes is explained here, generally the stability of alkenes is directly proportional to number of alpha hydrogens or number of hyperconjugate structures. More hyperconjugate structures, more stable. More stable alkene means here it is a less reactive in hydrogenation reaction. Okay, now here for suppose this CH2 double bond CH bond CH3, propene and CH2 double bond CH3 and CH3, 6 alpha hydrogens for this one, 6 alpha hydrogens for this one, 3 alpha hydrogens. This is the more stable, that means less reactive in a hydrogenation reaction. Okay, or we can explain the based on this hydrogenation process is adsorption based reaction. Okay, so that alkene must be less sterically hindered. Okay, so actually here this is a metal surface, this is the hydrogen. Okay, that alkene must be sterically less hindered. Okay, if the alkene is less sterically hindered, so then easy absorption of this hydrogen from the metal surface takes place. Okay, so here in this case, less substituted alkenes are more reactive in hydrogenation reaction. So in this case, B is more substituted here. Methyl here, methyl. Okay. Next, C, one methyl is there. Here, A, one methyl is there. Which pi bond will reduce first of all? Here, D, here in this case, we can see it is a less substituted actually. Okay, here for this one, for the B, here CH3, 6 alpha hydrogens, here 2, 10 alpha hydrogens. For C, here 3 alpha hydrogens, here 2 alpha hydrogens, here 2 alpha hydrogens, so 7 alpha hydrogens. For this one, 2, here 1, 3, here 3, 6 alpha hydrogens. Okay, for the D, here 3 alpha hydrogens, here 1 alpha hydrogen, only 4 alpha hydrogens. So it is a less substituted one. So here D readily attacked by the H2, okay, from the metal surface, and least one is a B. Yeah, B is a least reactive. Okay, so the more reactive double bond, that means here about after hydrogenation about this double bond, that gives a more heat of hydrogenation. Actually less stable alkene, it means a more reactive alkene produce a more heat of hydrogenation. Here heat of hydrogenation process is the exothermic process. So heat of hydrogenation of alkenes inversely proportional to stability. Okay, so it is a less stable double bond C double bond C, it has a more heat of hydrogenation. Okay, more negative heat of hydrogenation. That's it. And next, one more question. It is a Wurtz reaction actually. It is a intramolecular Wurtz reaction. Okay, sorry, intermolecular Wurtz reaction. So here in this case, the CH2, Cl are not adjacent to each other. In the presence of sodium, dry ether Wurtz reaction. So in this case, by the combination of those two reactants, so you can see like this here, the CH3, CH2Cl, Cl, here next, here Cl, here Cl, here in this case it may be CH3 like this. Okay, so sorry, here CH3 adjacent to the this one CH2Cl. So here by removal of this one you can write the simply ozonolysis product, sorry, Wood reaction product. So the product is A. Okay, A may be formed, or in this case here we can take the combination of these halides in this manner also. Cl here, CH3, this one Cl, Cl removal. So here in this case this product is also formed in a Wood reaction. Okay, here it is a intermolecular Wood reaction. For suppose here in this case we can take like this, here Cl, here this Cl. For this one, here these two are adjacent each other, so there is a intramolecular Wood reaction takes place. So here the cyclization takes place, the 5-membered ring in this case. Okay, that's it. Thank you for watching. Please subscribe my channel for more videos.